All right, so this is going to be chapter 9 of Giancoli, problem 1. And let's just get right into the solution. This is the problem about the tree sapling with 3 forces, and it's being stabilized. Essentially, we're given 2 forces, and we have to find the third. We have to find the magnitude and the direction of the third force. So this is just a force balancing problem. If the tree is not accelerating, then the net force is going to be 0 in all directions. So this is what I'm going to call our stability condition. So we can say the sum of all forces is 0, and this is going to be very important to utilize for different directions. So it's actually both x and y, right? When we say some of the forces is 0, it's really all of them, but to be specific, it's x and y in this case, right? So what we can do is we can work with these forces pulling the tree in different directions with a, let's draw our little coordinates right here, with a being here. I'm just going to label them not with letters and not f's. A being here, B being there, a little bit larger than A, and then C being here in quadrant 3. So what we want to do essentially is go through summing the forces in the x or summing the forces in the y, or actually both. So let's just go ahead and get right into that. So we know that the sum of the forces in the x is 0, and now we want to look at our diagram and essentially just plug in stuff to the left side. So we want to add the forces up. If we call this the positive direction, if we call the right direction to the right-hand side is the positive, then A is going to be a positive force, and it has no angle associated with it off of the horizontal, the positive horizontal, so it's multiplied by cosine of 0, which is just 1. So you'll just have FA as the first part, and then we want to add 2 other forces. I mean, these forces are kind of in both x and y, so they're going to show up in both equations, but whenever we do some of the forces in the y, you'll see that there's no reason to include a since no part of it is in the y direction. But yeah, the next thing that we want to sum is the b force, but we only want the x component. We don't want the y component, right? Because there's a y component and there's an x component for both of these, for both b and c forces. And we have to take into account this angle, right? We can't forget that this is 105. We also can't forget this should be, let's just designate this one from the negative horizontal to C as theta, and from C to the positive horizontal as phi. So we can use those later. And we also want to note that, half a circle's angle is equal to a semicircle's angle is equal to 180 degrees, and that's essentially what theta and phi are summing up to. So to come back to our sum, the x component of b is going to be basically FB times the cosine of 105, the angle that's associated with B. Other than that, we can add that we know that there's an x component of C, but we don't know what it is yet. So let's just call it FCX. So we can actually find what FCX is, right? If we just do some algebra, FA will go on the negative or on the other side of the equal sign, and so will FB. So both of these will go here, right? And so we just have minus FA minus FB times cos of 105, right? And so this is going to be essentially, you should have the numbers, but it's minus 385 newtons subtracted by 475 multiplied by cosine of 105. So this is going to end up giving you minus 262.1 newtons. So we have FC. Now, keeping this picture in mind, I'm just going to open a new page and do the y there, the sum of the forces in the y. This one's easier, only 2 components, right? Because we have the up from B and the down from C. So we're going to say FB, and now since we're dealing with y, we want to use sine instead of cosine. So FB sine of 105 plus FCY. So we don't know much about C yet. We want to find out, right? And so it turns out it's just the negative of this, just the negative of FB sine 105, which If you do the calculation, put it in your calculator, FB is 475, so 475 times sine 105, and the negative version of that should give you minus 458, so it's not a very big change. Minus 458.8 newtons. With these two, we can find what FC is, because there's an equation called the distance equation. It's very similar to Pythagorean equation. So if we have an x component and a y component, and we square both of them and add them, then take the square root of that, we should get the diagonal, if it's diagonal, whatever it is. So if there's an x component, it will get more in the x, and y more in the y, so on and so forth. But you can plug these numbers in. So basically just take FC x here, 262, FCY here, 458, and square both of them, add them together, take the square root, and you should end up with something like 528. Yeah, 528 newtons. To find theta, it's another very similar thing to the distance equation. Well, you should know it as well as knowing the distance equation, that the tangent of any theta is equal to usually the y over the x component, which is, in this case, it's going to be FCY and FCX, right? So this is more like an arrow. It's not actually equal, but tan theta is actually equal to this here, right? In our case, but generally it's equal to y over x. So let's just say FCY. Let's maybe erase a little. Okay, well, we'll leave it. Just know that this is FCY over FCX, and so essentially you're just going to say that theta is the tangent inverse of this combination, FCY over FCX, and that should give you a number about 82, right? Oh, sorry, no, 63. That's another problem. Oh, that's, yeah, there you go. Okay, so it should be about 60.2 degrees, or 3 degrees, 60.3 degrees. Then if we want to go from so theta is not going from the positive horizontal, so we don't usually use this kind of this angle. We actually want phi in this case, right? So since we want phi, we just want to say phi is equal to 180 minus theta, right? Just some algebra, moving theta to the right side. And we know that theta is 60, so I mean this is just going to be basically 120, right? It's going to be a little bit lower with that point, with that 0.3 coming in. It's around 120. It should be about 120. And so this concludes our answer. We can see from the picture, right, that phi is about 120. You know, it's like well, I kind of drew it in the middle, but it's a rough drawing, not exact, right? But we got it in. The point is that we got the force from C into quadrant 3, which is what we needed, and it has a magnitude of 528, which should balance out that force, the forces of acting on the tree. Okay, thanks.